for Material Studio at BioVia, formerly known as Accelerus. I'd like to welcome you today to the webinar entitled The Interface Force Field for Accurate Simulations of Inorganic, Organic and Biomolecular Compounds. Material Studio is BioVia's predictive modeling and simulation solution for understanding how materials work. It can be used to screen properties of a wide range of materials and to improve your understanding of why a material behaves as it does. It is with great pleasure today that I am honored to introduce Dr. Hendrik Heinz, who is an associate professor at the University of Akron, and he is also a research consultant. Hendrik earned his PhD in material science and engineering and a master's in science and chemistry from the ETH in Zurich in 2000. His research interests are computer simulation of inorganic and bioorganic interfaces, biomaterials and tissue engineering, polymer composites and mineralogy. If you have any questions during the presentation, please type them in the chat window to the right and we will answer them during our Q&A at the end of the presentation. The recording of the webinar will be sent out to everyone who registered. So with that, it's with great pleasure that I hand over to Professor Heinz.
Hello everybody, and thank you very much Stephen and Audra to enable this webinar today. So as already mentioned, this webinar is about a new simulation capability that we have developed in our lab, which we call the interface force field. And it is mainly actually a resource to combine the simulations of organic and biomolecular interfaces with those of inorganic compounds, which have been previously requiring two separate platforms, or in part the parameters for the inorganics, they were not very reliable or unavailable. So let me see if I can go to the next slide here. Okay. So essentially, what this platform enables, and I will go into more details, is looking at materials interfaces. I mean, basically trillions of new interfaces between certain inorganic components and all the huge variety of biomolecules and organic molecules that are already available as part of Material Studio software and also Discovery Studio software. So in a nutshell, so I will explain this in just a little more detail in the introduction, then go through applications to highlight where this capability is useful. Then go a little bit to the theoretical background, how can we accomplish these improvements, and then also how can we use this resource with Material Studio. So the first part, again, what is this interface force field and what can it do for us? So it is meant to be a uniform platform for classical simulations, basically a uniform force field that works both for biomolecules and inorganic components. And actually, as we know, if we simulate structures in chemical accuracy at a scale between 1 and 100 nanometers, or maybe even up to 1,000 nanometers, then we actually only can use classical force fields because, say, the DFT methods, they would not allow access to those larger length scales, and also coarse grain models or mesoscale models, they don't have the atomic resolution. And so what we do here is we're using a uniform Hamiltonian for both the organic and the inorganic components. Based on the energy expression of PCFF, and then in part we've also done this for CVFF and for CHARM. They are not yet implemented. So what we currently have implemented is the PCFF. And I mean, what it really enables is that we have thousands of or millions maybe of different inorganic compounds and specific surfaces and nanocrystals that can be handled. And on the other end of the spectrum, we have billions of proteins or biomolecules or different polymers and combinations with solvent and ionic strength. And we can now really handle them all in one platform. Before, a lot of the inorganics just it wasn't really accessible, or the interfacial energies were not thoroughly validated. So this is what is new about this platform. And then, if you look at length and time scales, just to sort it into context, right? We have here atomistic methods that this resource is about. Then on the larger time and length scales, we have coarse-grained or field-based methods. And then on the smaller end, we have quantum mechanics, which is great to tell us about electronic structure and reactions, bond breaking and formation, and so on. Now, the key elements of the parameterization in the force field, or as you say, basically the chemistry that we put into the models. So they are, based on the polarity, which we represent by atomic charges. And I will explain later what exactly we are reproducing here. Then another aspect is, we reproduce structural properties, like whenever there are X-ray data for those minerals, we want to make sure they are reproduced. And then surface energies and interfacial energies. In all these categories, including also for the electron density distribution, there are experimental data available, and we are really going to the experimental data because they are far less associated with uncertainties than, say, data computed from electronic structures, so especially electron densities and surface energies. And actually, this also careful interpretation of the parameters in the end gives us an improvement in surface and interfacial properties and by about an order of magnitude or so compared to previous models. So for this reason, we have really accurate parameters for those inorganic compounds that are currently included, and we can simulate all these different interfaces. It actually fills a blind spot from the viewpoint of laboratory investigations, since imaging and in situ monitoring is particularly difficult for soft matter, and even for hard matter or not entirely crystalline structures such as metals. It's a challenge, and here the simulation really helps us add these capabilities. And then also we see this as a process, right? There are a lot more compounds that we wish to include, like different types of metals and with some semiconductors and further polymers and oxides. And that's in part also possible, to do through community users. Now, what is so particular as an advance in interfacial properties? So this is shown here. It's a very busy slide. basically showing certain types of parameters or properties that we are reproducing very well. Like here, cell parameters, for example, the agreement with the experiment is usually better than 1%, 0.5%. Then cleavage energies and surface tensions, the agreement between experiment and what we see in the interface force field is very good here for several clay minerals. And actually other force fields that are available or have been used, including, for example, here the clay force field. They have much larger deviations in interfacial properties, so that accurate binding energies of molecules or self-assembly of different building blocks, they can be much more accurately understood using the interface force field. Then we have also a number of silicates and aluminates in cement as part of our package. So again, here then cleavage energies are well reproduced. Mechanical properties are very good. Interfacial tensions, also water-solid interfacial tensions. Basically quantitative as far as one can see. And then there are metals also. Currently we just have FCC metals included. And there are a number of properties that match up very well. So this list is, one can see more in this article. So it also includes gypsum and apatite, and I will come to some of those later. So overall, what we can say is maybe from a graphical snapshot, now we can look at actually any type of compound in the periodic table and develop an interface parameterization. We can see here, some of them are aqueous minerals, like panel J, or others. They are, here A, that's the silica surface, or F, that's some metal, or G is a nanoparticle, palladium nanoparticle. We can integrate parameters for any compound. It does take some effort, though, for a new type of compound to go through the validation and the protocol. But once that is completed, and it's a very dependable resource for these types of materials. So here we have, for example, layered silicates, currently included, FCC metals, silica, bulk, and also the different surfaces as a function of pH. The surface chemistry changes quite a bit, and this is something we capture. Then apatites, cement minerals, calcium sulfate, and we also worked on some polymers. This is, for example, taking into account the gauge effect and particular folding preferences that are represented in the model. Now, how to use this? I don't know if this web page was updated. So we can actually use it directly from the web, or now as it is implemented in the Biovia web page, because this will contain the force field files. They can be directly used in Foresight, and then there is a list of surface models that can be directly imported. Key aspect, we will come back to this later, is that we have defined the atom types and charges for these different minerals, and they should be used as is. So one should not go with the automatic typing and charging, because the charge engine and the typing engine sometimes cannot handle these complex chemical environments that are present in the materials. For that reason, we should use the atom types as they are provided, and also the charges. It is easy, say, to customize this for slightly different structures. But just going with the charging protocol that is in place for this type of compound. And then, well, it can be run with Foresight and Discover. It's also possible to run this with other simulation engines, so there is no actual limitation. And then so we have currently the PCFF interface force field there. We also have a charm interface version that perhaps will transition into Discovery Studio also soon. They are working. There's also a CVFF interface version that will be, it exists as an FRC file, but we will make an OFF file also for usage in Foresight. Now, actually this was already quite an overview of what it is meant to do. Now I would like to go through some applications. How can we use it? What kind of information can we gain from this interface force field? Now, there are several areas where we have already shown that it's actually quite useful. For example, recognition of biomolecules on metal nanoparticles, also even predictions of catalytic activity because there are reactive extensions possible. And then we have looked at assembly or biorecognition of silica surfaces and of apatites and some cement minerals. Now the time is short to go into very much detail for each, so we want to keep it perhaps a little bit higher level, but also show some specific details of the information that we can actually access. Now, if we look at the first part of the example is recognition of biomolecules or analytes on metal surfaces, and this can have a lot of applications for sensors, for new catalysts, electrode materials, assembly of new structures for nanoelectronics, and also for therapies like cancer therapy, with metal nanoparticles that are decorated on the surface to dock onto specific types of cells and then terminally, for example, induce a treatment. Now, practically, in terms of what simulations are we running, we can imagine the different types of surfaces, like flat surfaces or nanostructured surfaces or nanoparticles, and then compute some binding energies with those specific biomolecules or actually like representative models of cell surfaces. And of course, such simulations can be run just atomistically, but also using other techniques in conjunction. And now, if you look at specific data, then we can have peptides in solutions. We can have those peptides positioned on the surfaces of metals, different facets, any facets possible. And then also in part, I don't know if this is playing. Is this playing? Yeah, we can see some dynamics of assembly of the molecules on the surfaces. What kind of sites they would cover, and then determine some catalytic activity out of that. Now we can see actually also that binding on those metal surfaces is sometimes really, or generally is very strong. So it needs also good annealing protocols and such kind of technical refinements. A key observation actually was that from those simulations, actually a new discovery, that such organic molecules, they coordinate preferentially epitaxial sites. So the atoms in the top layer, they are represented by larger spheres here, and then the smaller spheres and the crosses, they represent the subsurface layers that are equivalent to the epitaxial sites. And of course, there's a trade-off between conformational flexibility and also competition between water and those molecules. But in the end, the majority of polarizable atoms coordinates the epitaxial sites. So this is actually here for a gold surface. This is a platinum surface, and that's got a lot of interesting implications. It's also very consistent with experimental observations that in general, chain molecules here, they have a preference for 1-1-1 facets. Now we see this in terms of more negative adsorption energies. And actually on 100 surfaces, this preference is not as strong. It also differs a little bit depending on peptide sequence. So somehow from this information, yeah, we figured out what is the essence of this selective recognition of biomolecules on metal surfaces. And here, this is a little bit animated, but shows how, for example, phenyl groups and guanidinium groups are a very good match to the 111 facets, whereas maybe some conjugated molecules, they are better fit to the 100 surface. A phenyl ring would not be able to coordinate these epitaxial sites very well, and if we have 110 facets that are also very common in metals, then actually there's a much broader spacing here that leads to less specific attraction or specific upright ordering of certain molecules on the surface. So there's more information that one can see really in the papers, but what it shows is that really the binding strength increases when polarizable atoms in those molecules coordinate epitaxial sites. Like here, we can see this for arginine, which was also experimentally identified as basically the strongest binding amino acid to gold surfaces or other noble metal surfaces. Yeah, and so we have done extensive studies actually that help us, for example, identify this ranking here of all amino acids and their attraction to the metal surface. I think this is more information to just support. I mean, if we compare, to experimental evidence, then we can say that we see the same relative strength of those amino acids in terms of their surface attraction in the computation and in the measurements. Then also we see that different metal binding peptides are similarly attracted to silver, gold, or palladium 111 surfaces, which is related to this epitaxial type of adsorption. And there are further data about mineralization of metal nanocrystals and so that are consistent with what we have actually explained by the computation. And also, we made some comparisons here to some earlier data. Actually, this one on platinum shows very nicely how alkanes in condensed phase would be packing on platinum surfaces. They fit into these epitaxial sites according to low energy electron diffraction data by a homologized group. This is in the end what we see in the simulation and what we can quantify in the simulation and also predict for different types of molecules and different solution conditions. So yeah, actually then those methods here, we have also applied them to make some specific materials predictions. For example, by computation of binding energies and so forth, we were able to say that if we have phenylalanine containing peptides versus some other less facet-specific peptides, the attraction to 111 facets increases a lot. And then experimentally by our collaborators at UCLA, the group of Yu Huang, it was actually shown that you can change the nanocrystal shape if you use those selectively designed ligands. So instead of, say, cube octahedra, you can make tetrahedra, or instead of cubes, you can make tetrahedra, just by a single mutation in that peptide sequence. The same works also for non-biological molecules. If you add a phenyl ring in here, then you have a strong driver to support the formation of 111 facets. Yeah. So some other insight that we can gain from these models is if we have actually nanocrystals of a different shape, then we can see how the adsorption of solvents or other molecules depends on the location on the facet. For example, water molecules that are adsorbed to the center of a nanocube. They have a much longer residence time, a much stronger absorption energy than, say, water molecules at the edges. And that in turn also determines or causes some changes in competition between selective biomolecular ligands and water to those different surface features of nanoparticles. And yeah, here in particular, you can see that maybe this peptide called T7, it's not really attracted to the center of the facets, but it can be attracted to the corners of these facets because the mobility of water molecules here is much higher. So there are some really interesting and new details that we can see, and we have also shown in collaboration with laboratory efforts that, for example, we can explain even the selective formation and even concentration dependence of shape selectivity of nanostructures using this model. Like here, for example, cubes only formed at intermediate coverage or intermediate concentration of peptides in solution. And well, in the model, when we, for example, compute the facet coverage as a function of peptide concentration and so on, we in fact also see a maximum of stabilization of 100 facets at some intermediate concentration that correlates with the yield of those nanocrystals in experiment. There are also other correlations between yield and size. The binding strength determines what is the equilibrium size of those nanocrystals. And yeah, I cannot show all these examples, but we actually did look also at understanding the origin of the formation of single crystal nanocrystals, like shown here, versus twin seed crystals. And it was possible to really figure out that certain ligands have significant preferences, for example, this one, towards a twin seed versus others just, well, have about the same recognition for twins and single crystals. And then also, again, this correlates with the experimental observations. And of course, it needs to be also seen in concert with kinetic observations, because in the end, okay, crystal nucleation and growth are certainly controlled by kinetic factors as well as by certain thermodynamic factors. However, the correlations are extremely good, and I mean, here this could be a summary for this type of correlations. That we can calculate the selectivity to specific facets, which will then correlate with the recognition of specific peptides, using phage displays that is found in experiment. And we can determine things like facet coverage and relative facet coverage that correlates with the observed shape and yield of nanocrystals. We can look at the spatial location also on those facets and some specific distances, which provide some extra atomic level information, actually rational for the observations. And then binding energies will correlate with measured binding constants and the size of nanocrystals. And then we can also look at assembly, actually, specifically on as a function of nanocrystal properties. And that, again, will tell us or guide us how we should perhaps tailor those nanoscale structures for a certain desired outcome. So I think this gives an idea for this whole area of metals, and in a very similar way, the same techniques are applicable for oxidic nanocrystals and structural growth. So I want to just show a few ideas about silica here. It's used very widely for catalyst support and as carrier for drugs and in separation media. And Also actually, it's interesting to see if we could synthetically make well-organized hierarchical nanostructures. And also, this is currently still a bit of a challenge. Now, the basis to maybe gain some understanding is getting insight into interactions of peptides with those surfaces. And for silica, a key aspect that actually had not been considered earlier is that those surfaces have a wide range of variability, both as a function of surface, temperature, surface chemistry, and then also pH conditions. And then selective adsorption, in summary, is controlled by 3 different types of processes. One is possibly in solution ion pairing. That depends on the density of charges on the surface. Then hydrogen bonds can occur, and then also, depending on what kind of molecule interacts with the surface, sequence-dependent relationships. That's depending on the stiffness of the backbone and the presence of specific residues that induce either hydrogen bonds or ion pairing type interactions. Now, what does really matter a lot is this density of sialoxide groups. Depending on even the type of silica, so at pH 7, this can be between 0.2 and 1 ionic groups per square nanometer, which is a factor of 5, and this is a huge game changer when it comes to selective adsorption of surfactants or biomolecules or polymers. So we have tried to, we have actually solved this problem in terms of modeling, because we took experimental data into account as a function of pH and also particle size. Surface ionization varies a great deal. And also we made accordingly models that represent these different possible surface chemistries. No ionization, some ionization, then some type of quartz-like surfaces with Q2 environments. So there's a whole database now available, and according to the type of silica that's of interest, we will, recommend in choosing one of those surface models or making a customized surface model, and then accordingly set up the calculations along with the new force field parameters also for silica that we have developed. And those force field parameters, for example, they reproduce the hydration energy that was measured here. They also reproduce contact angles of water and silica for those different environments, at high temperature, if they are annealed, from Q3 to Q4. Then also we looked at the density profiles of those electric double layers, and actually, there we found some interesting correlations of the amount of those dissolved sodium ions, the ones that would diffuse more into solution, and the measured theta potential in experiment. So those correlations are really good, both as a function of pH and then also as a function of particle size. The different particle size here is then reflected by, for the larger particles, we have a mixture of Q2 and Q3 environments, and then medium size is more Q3 environments, and then smaller particles have a little bit less ionization. But those trends are actually really interesting, and they allow quantitative comparisons to measurements. So, for example, if you look at specific adsorption of peptides, then we may have, at pH 9, for example, ammonium groups like here, lysine group is binding very strong to the surface through ion pairing. If we have a lower pH with less ionization, then suddenly other residues join, and at low pH, actually, it's almost like a hydrophobic depletion interaction that was also observed in an experiment that leads to the binding of several residues, even though it's weaker than the ionic interactions. And if we say do this, we did a number of studies here, for differently charged peptides and different pH values in the experiment and in the simulation. We see a very good agreement, so we can actually predict how strongly peptide binds as a function of silica surface structure, And also the binding free energies, they are not shown here. They correlate with measurements in the experiment. They are in a range of -1 to -8 kcal per mole for these systems here. So what this shows is that we get really some atomic level information. Also, we checked some correlations here with NMR, 2D NMR spectroscopy. If you have a strong peak in NOESY in the 2D NMR spectrum, then we can actually in the simulation see that the internuclear distance between those protons is at the small end. If you have a if you have a medium strong NOESY peak, then the distance is a little bit larger, and for those weak ones, the distance is even larger. So even as a time average over 5 or 10 nanoseconds, we can actually almost atomically resolve those interfacial structures. And that's quite exciting. I mean, I think this has not happened before. And the initial efforts to, for silica parameters, they date back, I think, to the work of Hill and Sauer in the 90s. They couldn't make at that time a force field that would actually be even structurally stable, and surface ionization, all these things, they haven't been taken into account until we actually came up with our models. Now, another area for applications also can be appetites. So they are really interesting in bone and teeth, and also for biological calcification, like in coronary artery disease or some other case like that. And well, we came up with models for the apatite nanocrystals and the different cleavage planes. And also what matters exactly here is this dependence on pH. Current or previously, I don't know if this is highlighted here. Yeah, actually, some prior simulations, they have been unrealistic in the sense that there actually was no surface protonation assumed, which is pH more than 15. That's would lead to cell death immediately. So what we have in our models is then, according also to experimental data, surface models at those more realistic pHs that are included in the in the database that is shared on the community website. And with that, say we are able, as a function of different pHs, to look at in the end, specific recognition of drugs and biomolecules. So that's what we're really interested in. But also on a more fundamental level, I mean, first you can see here there are big differences both in the types of residues and in the binding energies when the pH changes. On a more fundamental level, also cleavage energies, they are tremendously dependent on protonation of the surface. The more it's protonated, the lower it is, and the correlation with experimental data is pretty good there. And then also hydration energies or immersion energies in water, also expectedly they would change a lot when you have different degrees of protonation. So this is all, I mean, well reproduced in the models. And besides also here, lattice parameters and elastic constants are doing very well in comparison to experiment. So this is representative also of the other minerals that we have incorporated in the interface force field. Yeah, perhaps a brief note. Well, one more slide is here to show what we are currently studying also in one project. Here, this concerns the interaction of different drug molecules, like those used against osteoporosis, with hydroxyapatite nanocrystals or nuclei and specific facets, because there have been certain hypotheses that they will block the growth of certain facets or block the dissolution of certain facets, and this is something we can actually test now in quite a reliable manner through those simulations. A last example, because we will also not be able to cover everything, but I mean just in principle here, for cement minerals, the main component in Portland cement is tricalcium silicate, and there are a lot of current gaps in knowledge how hydration happens, interaction with polymers happen, how even the cohesive forces can be influenced during grinding in a ball mill, which consumes a lot of electrical energy. And so through these models we developed, that meet all those interface standards of structural reproduction and reasonable cleavage energies, we're actually able to explain the mechanism of grinding aids that are used in cement plants for cement grinding, even able to make some predictions of how we should design new molecules to increase the energy savings in those applications. And then also we're looking at hydrated surfaces. We have models for turbomorides and so on included that can describe the interaction with polymers and aqueous solutions, hydration reactions of cement. Now a few minutes are left, I guess, for explaining how we get to the accuracy, how we go about our parameterization approach. And so a key choice that we made is among different energy expressions that are available, we preferred harmonic energy expressions because they are working fine for all the biomolecules and organics, and they do have non-bonded terms. And so for minerals, we can use this expression, and as all the examples so far even have shown, it's working just fine. So that, if we were going, say, with Buckingham potentials, then we have some difficulty in compatibility to look at these kind of interfaces. If you use many-body energy expressions like EAM and modified EAM for metals, then we cannot really pair this up with organics. And actually, also in quantum mechanics, we don't have many-body interactions. It's all described by pairwise interactions, Coulomb and van der Waals type. So this is a choice we made. Then we have this, for example, here in PCFF, this energy expression with bonds, angles, and then non-bond interactions. For the minerals, we need most of the time bonds and angles. We don't need those types of terms. Sometimes when actually the bonding is more ionic than covalent, then we also don't have bonds and angles, and we would just have van der Waals and Coulomb interactions. Now, as I mentioned before, a key aspect is describing the polarity and interfacial structure. The polarity in terms of atomic charges really reflects the electron density. It's a coarse-grained model of electron density. And at this point, say we stick with atomic charges, but we also have developed certain models that have a more detailed representation of point charges that are more located where the orbitals are actually located according to electronic structure. So this is useful to reproduce crystal structures of BCC metals and such. But that's a work in progress. Now the protocol that we usually go about for the parameterization is starting with an X-ray structure, defining atom types. That's important part here. Then obtain those atomic charges, and I'll explain how we do this, because it's not a black box DFT calculation. That would not give a good accuracy. Then we assign initial Lennard-Jones and bonded parameters, then test computational density and geometry. If needed, then adjustments can be made, and then evaluate the surface properties, and then do some secondary validation and end up with the final parameters. Now, what we really pay attention to is interpretation of the parameters. So we don't actually have any numerically fitted parameters that are not assigned a clear chemical or physical rationale. So the first thing to check off is that, well, it's widely compatible with different energy, I would say, with the existing energy expressions for organic compounds. Then atomic charges, they have a huge impact on surface interface properties. Similarly, the van der Waals or Lennard-Jones type parameters. And surface chemistry is important. As mentioned, the hydration state or protonation state and charge defects, they need to be assigned in agreement with what we have in the laboratory. If we want to make materials improvements, we have to feed available knowledge into the models first and then run the simulations. Yeah, well, then there are a couple other things that are easier to assign and have a clearly defined interpretation. Yeah, for the charges, we really look at experimentally determined deformation electron densities. They are available for a number of compounds. And then we also developed an extended bond model that relates atomization energies and ionization potentials and trends across the periodic table to the assigned atomic charges. Now we have so much chemical knowledge about reaction mechanisms and that usually are heterolytic and involve polarity. And then neighbors in the periodic table like carbon versus silicon, aluminum versus magnesium and so on, trends that really help us from several angles to approach this question of what should be that atomic charge to best reflect the chemistry of this compound and of all those atoms in the compound. And this is what we use, and there also we see that the accuracy of such atomic charge assignments is actually better than plus minus 0.1 elementary charges or less than 10% error for small atomic charges. And that is a huge improvement over using ab initio methods, because the spread in those methods can be sometimes factors of multiples, a huge uncertainty, and then when this is not properly implemented in the force field, then we end up with huge errors, up to such effects that we don't even have a stable structure in the simulation. Yeah. So here's a lot of data. I mean, for selected compounds that were analyzed experimentally in terms of electronic structure. So that's certainly a very important piece of our parameterization. And well, one also sees that by parameterizing different compounds of chemistries that are always in some form related, that in the end a huge amount of consistency between the individual parameterizations and also charges for, say, silicates of different type, or silicate versus phosphate or sulfate, in the end provide a real great feedback that our choices have been made precisely for this. So this is an extended bond model that we have been also using to put a good rationale onto those choices, using available knowledge. Yeah, validation of interfacial properties is very important, because then we have also data on how good a cleavage energy or hydration energy or a interfacial energy is reproduced. And most of the time we see, for example, if we reproduce a cleavage energy correctly, then instantly even the mechanical properties also, like Young's modulus or bulk modulus, are in very good agreement with the experiment. So by just validation of structure and interfacial property at, say, room temperature, a lot of other properties like mechanical or thermal also, heat capacities and such, oftentimes are very close to the experimentally measured values. So here there could be more examples for structural reproduction. You can see that for a range of minerals we get those cell parameters in very good agreement with the experiment. Then, as mentioned, the surface and interfacial properties, like here, surface tensions, experiment versus computation, even electrostatic and van der Waals contributions are fine, and they are neatly related to the atomic charges that are assigned. So now if we, for example, take here a formal charge of silicon, then this electrostatic contribution goes up by a factor of 16. And simulation would be no longer reliable. So these are just some key observations, and pretty basic observations. Another cross-check is also when we do use different energy expressions, because if we develop parameters for PCFF, we try to also develop them for CHARM, CFF, AMBER, and so some other force fields down the road. We overall see, I mean, with the minor changes that are needed because of different Lennard-Jones potential and so on, we see quite a consistent result in the end, say, for geometries and also for cleavage energies. The 12.6 potential usually is a little bit higher than the 9.6, but often that stays within the experimental error. And then similar trends for maybe the bulk modulus. It may be a little bit less with a thermodynamically consistent parameterization with 9.6 potentials, and a little bit more for 12.6, but then again, that's all within a 10% range of difference. Now, well, the time is getting a little bit short, but a few words how to use interface. So one key aspect is that the information is on the web. There is a database of all the surface models that have been developed. Now they can be immediately used, so it's ready for simulation. It doesn't need any typing, any charging. Actually, one can use directly the model, choose the force field, and run the simulation already. And then accordingly add water. If it's about interfaces, for example, add water, add the organic components to the surface or to the nanocrystal that's already in the database. For the water and the organics, automatic typing and charging can be used, but not for the inorganic components that we have in interface force field, because they somehow have not transitioned at this point into automatic typing and charging engines. So that's the only point to watch. And then also, any of these crystal structures that are provided, they can be modified. The surfaces can be edited. Any say corrugated surfaces or different shapes of nanocrystals, or also different surface chemistries can be implemented. So this is just like the surface model database is just a point to get started. And so for all these compounds that are available, the usage is really simple. It's just use the model, modify the surface, or change the size, change or construct a different facet, or build a nanocrystal or a porous silica structure using the model. If you add new atoms, just follow the same charging and atom typing scheme. And then add all the, say, organic or biomolecular or water components, and then, well, just choose your simulation setting and click submit or run. That would take care of the simulation. It's really thinkable, simple. Of course, if it was to be ported into other platforms using Material Studio to construct the input, that's possible, and then one just has to follow the instructions for those other platforms. Now, just to summarize here for the structural preparation, chemical identity, defects, pH, this should be all checked. This is important because the simulation will certainly have a different outcome if we change the pH value and we have a pH responsive surface. And then again, utilize the atomic charge and the force field types as they are given. If you expand the structure, just follow the same charging scheme. It's usually really simple, and follow the right force field type assignment. Material Studio is a great, absolutely really best platform for viewing structures, analyzing structures, analyzing the output. There is no better tool available currently. So, and then customize the surfaces for specific conditions and so on. Here you can see, for example, a nanorod of hydroxyapatite, so that can be constructed. For silica, as an example, this has probably is one of the oxides that has the most variety of surfaces. So, if the first thing is, think about what experimental system you want to simulate, and then accordingly choose a model. Quartz surfaces or nanoparticles that are large, they require a different area density of cellular groups and different ionization than, say, for example, regular silica glass, according to pH value, or an annealed silica nanoparticle. The surface model database actually includes more than 20 models already that customize these different conditions, and they can be used, and they can be also further customized as needed. Yeah. So then, of course, there should be a force field chosen. So usually this is now a PCFF interface. That's the one that's implemented as in OFF format, ready for calculations. Then we are in process to get the CVFF interface on and the CHARM interface for Discovery Studio, which would be really great to have. And then, just use the ready-to-run structures with Foresight programs, or Discover if you have the older versions. yeah, you could also run this in LAMS or in NAMD later on if you ever wanted to. Yeah, with that, I would like to thank everyone on the team and you know, a lot of really great experimental supporters and collaborators that we currently have, and funding agencies, various you know, institutions and companies. And so thank you very much for your attention, and yeah, I hope we can have enough time for discussions.
Thank you very much, Hendrik. I'm just going to launch a quick poll question for everybody, and then whilst we're doing that, then we'll take questions. Okay, so there's already quite a few questions come into the chat area, so we'll just hopefully rattle through a few of these, and we've got a few minutes left. So can this force field handle calcium hydroxide crystals?
Oh, okay. It's not been completely validated, but it's actually something in progress. So we have worked on portlandite, and it's also going to come out soon. You can use in part what we have for the hydrated tricalcium silicate.
Okay. Another question, which is regarding Discovery Studio, and basically is how easy is it to get it to work within Discovery Studio? I guess the whole question was that they didn't find the interface force field inside Discovery Studio, and that's because the interface force field isn't included directly in any Accelerus package, sorry, BioVia package at the moment, but they're available from the download center. I'll get this right. They're available either for Material Studio from the community site or from Professor Heinz's website for the rest of the force fields. I don't know, Professor Heinz, whether you have anything you want to comment on the actual Discovery Studio working properly.
Yeah, actually, yeah, I mean, this is something I think, you know, we're trying to get actually sorted out. It's just a matter, I think, of time. So we could, you know, I am completely happy to, you know, share and incorporate this into Discovery Studio. All that it actually would need is we have, you know, the CHARM interface version already, and it would have to, I think, just be offered as a force field to pick. Because it's the CHARM, it's the same as the CHARM force field, and with those added compounds. And yeah, I don't know. Maybe Stephen, you can actually much better evaluate, you know, what is the best way to share or how to make this available.
Yeah, I think that's something we'll probably take offline for now, just because there's quite a few more questions coming in.
Sure.
So, can I use the interface force field to run molecular dynamics of peptides on nickel titanium surfaces?
Oh, okay. That's a very good question. On nickel surfaces, definitely. Yeah, the nickel is there. Now, in titanium, we have not included at this point. So you would have to be making some assumption about the titanium. But we are, in fact, yeah, so we're working on extensions for different metals. They just haven't come around yet. But so you could, if you come up with maybe with a simplistic, depending on how detailed it got to be, but you know, if it's an alloy or something, then you have to come up how to represent the titanium. And first order approximation you might get along with the Lennard-Jones potential. Also, what we will do for titanium is something a bit different that includes some dummy atoms to reproduce the HCP packing. But you know, in first approximation, just to look at the interface properties, you could probably the nickel titanium surface use the nickel parameters we have and use titanium parameters as they might be available actually in PCFF. You know, in a reasonable approximation.
Okay, and there's a couple which maybe I can just answer very quickly. Well, where can we find all the different surface models? If you are a Material Studio user, if you go to the community site and search for interface force field, you'll find a zip file there which has all of the, which contains a study table with all of the surface models included in it. Alternatively, again, you can download them directly from Professor Heinz's website. Is there any limitation on system size while using Material Studio? The limitations tend to really be in, well, in terms of real-time use, a few 100,000 atoms shouldn't really be a problem. If you want to go any higher than that, then the usability may begin to decrease. And then I guess one last question: can this force field be used for biopolymers?
Well, the PCFF version, yeah, basically, it's meant to be a fusion, right, between between anything organic and peptides and the inorganic. So for biopolymers, I mean, what I most recommend is the charm interface version. But then basically the parameters for the biopolymers are exactly the ones in charm, or that you have in Discovery Studio. So what interface is adding is all these new inorganic compounds or certain new polymers. We also started making some additions for specific biopolymers.
Okay. We have one last question, and that is, and we may have to time limit you here on this one because it's a bit of a big question. What are the common techniques to simulate organic interfaces in the nanopores of organic complexes? Actually, looking at this one, it looks like a question that's maybe a more generic question for us to get back to you on directly, rather than using up the time on this call. So we'll respond to that one directly outside of this webinar.
Okay.
Okay. Well, with that, I would like to. We're on top of the hour, so I'd like to say thank you very much for your time today, for both everybody who's listened in and participated in the call, and also especially to Professor Heinz for his time and effort in both creating the presentation and giving us the webinar today. If you do have questions, you can either contact Professor Heinz directly, or if you want to, you can log them into the Accelerus community on the interface force field thread. And so, we'll be having a look at that. And I'm sure if we get questions in there, then I'll also be asking Professor Heinz to kindly look at that as well. So with that, thank you for your time today, and I look forward to speaking to you all in the future. Thank you. Goodbye.
Thanks.